The degrees of freedom are found by substituting the sample standard deviations, 2.56 and 1.81, and the sample sizes, 24 and 28, into the degrees of freedom equation. Simplifying the numerator yields the square of the sum of 0.2731 and 0.1170. Simplifying the denominator yields the square of 0.2731 divided by 23 plus the square of 0.1170 divided by 27. The sum in the red oval is the variance of the difference in means. The square root of this is the standard error of the difference in means, which will be the denominator of the t-stat in the next hypothesis test example. Hence, the degrees of freedom are 40.585. When this value is not an integer, as it is here, we round it down to the nearest integer, which in this case is equal to 40. Like choosing a smaller alpha, or a significance level, rounding down to the nearest integer widens the confidence interval. In hypothesis testing, rounding down is akin to choosing smaller alpha, which lowers the likeliness of making a type 1 error. Since the confidence level is 0.900, the significance level is 0.1000. Since confidence intervals have two tails, we divide the significance level by 2, which is equal to 0.0500. We use this value to determine which column of the t-distribution table the critical value is in. Since degrees of freedom are 40, the critical value is in row 40 of the t-distribution table. Thus, the critical value, the upper critical value, is 1.684, while the lower critical value is negative 1.684. Next, substitute the sample means, sample standard deviations, sample sizes, and the critical value into the equation for the interval estimate. The values in red font are the sample means. X bar 1 equals 29.8 miles per gallon. X bar 2 equals 27.3 miles per gallon. The critical value was 1.684. The sample standard deviations were 2.56 and 1.81 miles per gallon, while the corresponding sample sizes were 24 and 28. Subtract 29.8 and 27.3 yields 2.5 miles per gallon, which is the point estimate of the difference in population means. The margin of error is 1.051 miles per gallon. Adding and subtracting the margin of error, 1.051 miles per gallon, to and from the point estimate of the difference in population means, 2.5 miles per gallon, yields a 90% confidence interval estimate of 1.448 miles per gallon to 3.552 miles per gallon. The center of the following bell-shaped distribution is the difference in X bar 1 and X bar 2, which is equal to 2.5 miles per gallon. This is the point estimate of the difference in mu1 and mu2. At worst, M cars probably have 1.449 miles per gallon better fuel economy than J cars. At best, M cars probably have 3.551 miles per gallon better fuel economy than J cars. We are 90% confident that the difference between the mean fuel economy of the cars is between 1.449 to 3.551 miles per gallon. Because if we construct 1,000 of these intervals using results from 1,000 random samples, 950 of these intervals will contain the true difference in the mean fuel economy of the cars. That is, mu1 minus mu2 will be in 90% of all confidence intervals constructed. Since the confidence interval does not contain 0, M cars probably have better fuel economy than J cars. Can we conclude, using a 5% level of significance, that the miles per gallon performance of M cars is greater than the miles per gallon performance of J cars? The phrase miles per gallon performance of M cars is greater than miles per gallon performance of J cars represents the alternative hypothesis. Recall, N1 is 24 cars, N2 is 28 cars, X bar 1 is 29.8 miles per gallon, X bar 2 is 27.3 miles per gallon, S1 is 2.56 miles per gallon, and S2 is 1.81 miles per gallon. In step 1, we developed the hypotheses. Mu1, the mean miles per gallon of all M cars produced, greater than mu2, the mean miles per gallon of all J cars produced, is equivalent to saying mu1 minus mu2 is greater than 0. The latter statement is the alternative hypothesis, which indicates the test is an upper-tailed test. Also, D0 is equal to 0. Since the null hypothesis is associated with the word equals, mu1 minus mu2 is less than or equal to 0. In step 2, we determine the critical values. Since the level of significance is 5%, alpha is equal to 0.05. Because this is a one-tailed test, alpha is divided by 1, which equals 0.050. For this reason, there is only one t critical value, which is found in the column 0.050 of the t-distribution table. Recall that the degrees of freedom were 40 when we computed the interval estimate in a previous slide. The t-critical value is in row 40 of the t-distribution table and in column 0.050. Hence, 1.684 is the critical value of this test, which is positive because we are conducting an upper-tailed hypothesis test. Had this been a lower-tailed test, we would use negative 1.684 instead. In step 3, we compute test statistic t-stat. Substituting x bar 1 equal to 29.8 miles per gallon, x bar 2 equal to 27.3 miles per gallon, d0 equal to 0, sample 1 standard deviation of 2.56 miles per gallon, sample 2 standard deviation of 1.81 miles per gallon, sample size 1 equal to 24, and sample size 2 equal to 28, yields a t-stat of 4.003. In step 4, draw the distribution to help you reject or fail to reject the null hypothesis. The t-critical value is positive 1.684 because this is an upper-tailed test, which was determined from the alternative hypothesis mu1 minus mu2 is greater than 0. The probability that t is greater than the critical value of 1.684 is equal to the significance level of 0.050. The critical value defines the do not reject the null and reject the null regions. The null hypothesis is rejected because t-stat 4.003 is in the reject the null region because it is greater than critical value 1.684. At 5% level of significance, the sample evidence indicates the mean fuel economy of M cars is greater than the mean fuel economy of J cars. Another version of the difference in population means involves matched samples. A test involving matched samples compares a variable collected from the same group of individuals, states, or companies twice. Say before and after a policy is put in place, an advertisement is run on television, or a drug is used. Although matched sample problems test the difference of two means, it uses the method in Chapter 9 because the population standard deviations of the matched samples are assumed to be identical and the sample sizes are equal. In the example below, a Chicago-based firm has documents that must be quickly distributed to district offices throughout the U.S. The firm must decide between two delivery services, United Parcel Express and International Express, to transport its documents. In testing the delivery times of the two services, the firm sent two reports to a random sample of its district offices, with one report carried by UPX and the other report carried by Intech. The data on the next slide indicate a difference in mean delivery times for the two services. Use a 5% level of significance. The delivery times for UPX range from 7 to 32 hours. Delivery times for Intech range from 8 to 25 hours. The difference in delivery times from Chicago to Seattle is equal to 32 minus 25, or 7 hours. This means Intech delivery from Chicago to Seattle is 7 hours faster than UPX's. The difference in delivery times from Chicago to Los Angeles is equal to 30 minus 24, or 6 hours. This means Intech delivery from Chicago to Los Angeles is 6 hours faster than UPX. The difference in delivery times from Chicago to Boston is equal to 19 minus 15, or 4 hours. This means the Intech delivery time from Chicago to Boston is 4 hours faster than UPX's time. The remaining differences in delivery times range from -2 to 5 hours. The -2 difference suggests that Intech's delivery time from Chicago to Milwaukee is 2 hours slower than UPX's time. The point estimate of the difference in population means is found by first summing the 10 differences, which equals 27. Dividing 27 by the sample size of 10 yields the mean difference in delivery times of 2.7 hours.